Okay, it is now 4:05, and I think everyone's here too. So well done, everyone, for navigating the technology. This is 761 Mathematical Tools for Computer Science, and I'm David Rolnick. Thank you so much for coming. This is the first meeting of the course, and I realize that this is somewhat of an unconventional way to begin a course. We're doing the best we can navigating a completely digital course in these difficult times. This first meeting is going to be completely about logistics, how the course is going to work, meeting each other, what the subjects are going to be that we're going to cover, how grading is going to work, that kind of thing, and an opportunity for you all to ask questions. I should mention that it is being recorded. All of the class meetings are going to be recorded. If you have an issue with being recorded in your video, make sure to turn off your video. If you have an issue with being recorded in your audio, that's fine too. You can just post in the chat and I will read out what you say. So just be aware again that there will be a recording that will be disseminated within and possibly outside the class as well. I will cut introductions of students within the class if the video is going out outside the class. Okay, let's get started. So welcome. This class is intended to be a whirlwind introduction to important math that turns up everywhere in computer science. We're going to explore many topics, but the goal is really to learn how to reason mathematically about problems in computer science from the ground up, and how to prove statements formally when you need to. A bit more about the course. It's going to be about foundational math tools that you will use. And the goal is to be both really to provide math that is both interesting and important in a range of different contexts. I obviously don't know what everyone is going to be using these tools for, but I've found from at least my personal experience that these are some tools that are just very useful in computer science in many different contexts. Maybe more importantly than the specific tools that we're going to be talking through. So it's not just about theorems, it's also about mathematical ways of thinking about problems. So I'm a mathematician, and that has meant that I think in a particular way about different kinds of problems. And that can be useful, that can also not be useful sometimes. Sometimes thinking like a mathematician is not a good thing. But I hope that this course will give you the chance to be able to put on the hat of a mathematician or a theorist if you want to, if it's useful for solving a problem. And I think that that will be both interesting and hopefully rewarding. And I also want to cover in this course really cool and useful applications to different areas. Obviously, it's not going to be comprehensive. This is not intended to be a comprehensive examination of theory. Computer science theory is rather a lot of that. And we will only be covering some areas, and we will only be going very superficially into those areas. If you want to explore things more, I obviously would highly recommend that you check out any of the fantastic courses which are actually delving deeply into particular areas of theory within the department. And then finally, this course will also hopefully teach you how to come up with and write a mathematical proof. Which is a really useful skill, even if you're not actually going to have to write proofs for your research or your work. It will help teach you how to think in such a way that you could write down a mathematical proof. So these are the things which I hope that you will get out of this course. And I would emphasize that no background in theoretical math is necessary. Hopefully you will have seen some numbers before, but you're here, so I don't think that that's going to be a problem. The goal is not, this is not intended for people who have spent a lot of time thinking about theoretical math. If you have, then that's cool too. But you really don't have to have had a background in that. This is intended to sort of provide that way of thinking. And hopefully there will be things which are interesting for everyone, regardless of where you're coming from, what background you have. So with that, I'd like to start out with some introductions. I can start out myself. So my name is David Rolnick. I am a new professor here at McGill, and I'm a mathematician by training. I'm a professor of computer science. And my background is actually in discrete math, which means things like combinatorics and graph theory. I got my PhD in applied math, which was, in my case, math for understanding neural networks and deep learning, why deep learning works so well. And that's one of the areas that I work on still now. I work on both understanding deep learning, so the math behind, in particular, what kinds of functions neural networks can express and learn, really trying to provide rigor to a field that is often very experimental, and really work hand in hand with the experimental approaches to deep learning. I should mention that is not what this course is going to be about. I'm sorry if you were expecting any of that. There will be a little bit at the end in which I do get to talk about deep learning theory, but most of the course will not be about deep learning or machine learning theory. There'll be several lectures on machine learning theory, and we'll get to that a bit later. But mostly that's not what this course is going to be about. The other aspect of my work actually is not about theory. It is about applications of machine learning broadly to climate change. So both reducing the extent of climate change, that's reducing greenhouse gas emissions, and responding to the effects of climate change. So increasing the resilience of society to climate change. So those are the two aspects of my work: deep learning theory and machine learning applied to climate change. I'm from America. I just moved actually from Philadelphia. I was just a postdoc at University of Pennsylvania, and it's good to be in Montreal. We can go around and give introductions for those who would like to introduce themselves. I'd love for this to be a discursive atmosphere, so maybe we can just all go around, say our name if we want to say where we're from and what we're interested in or studying, and maybe something cool about yourself. Try to keep it somewhat brief. So I don't know, like 30 seconds-ish. We should have time. Something cool about myself. I really like singing opera, and I also like to look at moths. I'm actually working on applications of machine learning to identify moths automatically. Again, this will be cut from the recording, except from the in-class recording. Anyone in class will be able to hear these introductions. So if you want to go around. Okay. Well, thank you everyone who introduced yourselves, and anyone who didn't introduce yourselves, that's totally fine too. Welcome to the course. I hope that this can feel as close to us all actually being in a room together as we can, given that we're not at all in a room together and scattered over the whole world. But really feel free throughout the course to, there is a raise hand function. We're a little bit too large so that people can actually just step in, but please feel free to write in the chat or raise your hand and I can call on you and you can then speak any questions. That goes for this class and for future meetings of the course. So I really hope that this will be, there will be a bunch of discussion. Let's go into some of the logistics of the course now. First, an outline. What are we going to cover? You know, you said that you're coming from all these different backgrounds, and we're not going to cover relationships of math to all of those, but we're going to touch on a few different areas. So first, this is the introductory class. We're first going to start out by thinking about proofs. What a proof really is, how to think about math problems, how to solve math problems, how to write up a proof. What even is a proof? That's going to be next class. It's going to be on Friday. Then we're going to have a few class meetings on different kinds of proof techniques and where they might show up, why they might be relevant. So mathematical induction, which is really useful for proving things about, for example, sequences, recursion, stuff like that. Contradiction, which turns up in a lot of different areas, but for example, in theory of computation. Other proof techniques like monovariance, working out when an algorithm terminates, and inequalities. And really just trying to get a sense of what are some of the general techniques that you might be using to prove things rigorously with math. Then we're going to spend some time going into different areas of math and the particular kinds of thinking or even results that you might find useful from these different areas. And we'll try to spend time delving into a few things a little bit more deeply rather than getting a superficial understanding of a lot of things. That we'll probably also be doing that because there's a lot of math out there and there's a lot of combinatorics and there's only so much that we can delve. We're going to look at combinatorics, so some basics of binomials and combinatorial identities, graph theory, what graphs are, trees, Hamiltonian cycles, Eulerian cycles, things like that, colorings. Linear algebra, just an introduction to vector spaces, matrix products, determinants, SVD, stuff like that. Some more linear algebra, going into the meat of like matrix norms and random matrix theory, which turns up surprisingly often is actually like really never taught, I find. Even to mathematicians, it's often never taught. I wish I knew more about random matrix theory. More graph theory, going into things like random walks. Now that we've covered linear algebra, we can go into things like graph Laplacians and spectral graph theory and where that shows up and why it's interesting. And hopefully tying some of these things together with when you might actually use this stuff. Though we'll also see some of that a bit later on when we're moving away from the math towards the applications. Moving on with different mathematical areas, going to calculus. So starting out with like what a limit is and derivatives and gradients and stuff like that. And all of these things, even if you've seen them before, we'll try to go from a bit more of a theoretical perspective and really prove why some things are true, or at least provide intuitions for why things are true and make mathematical sense. You'll find probably that the way that things are presented mathematically is somewhat different from the way that they're presented if you're just trying to use them sort of as an engineer. So I think it's really useful to go back to some of these concepts and really understand sort of where they're coming from mathematically, why they're meaningful. We'll go to Taylor series, big O notation, and asymptotic analysis, and why calculus makes that kind of thing really, really interesting and doable. Then go into probability, which is another huge topic. We'll start out with things like Gaussians and entropy and mutual information, Kale divergence, and how all these things are related. And then move on into things like Bayes' theorem and variational inference and MCMC methods. These are, again, lots of different things, which you could have an entire course on MCMC methods, for example. And we are not going to go into all the details or try to cover a huge variety of things, but I'd love for you to see a sampling of where these kinds of things come up, how they're useful, and what really motivates them. So why these are interesting, why does it matter? We're going to move on into slightly more applications with linear programs. So linear programs can be thought of from a math perspective or from a CS perspective or from many other perspectives too. Starting out with just what is a linear program, primal and dual formulations of that, discrete geometry, ways to think about that from the perspective of discrete geometry, which is sort of the more mathematical side of this. Going on into more sophisticated stuff, like algorithms for solving linear programs, the simplex method, ellipsoid method, and so on. Moving on to different kinds of programs, semi-definite programs, quadratic programs, and integer programs too. Going on, again, continuing into a bit more of the algorithm side, looking at spanning trees and shortest paths, so different graph algorithms and where our graph theory can actually be useful in some of these contexts. Likewise, max flow problems on graphs. There are a lot of cool things to look at with max flow. Looking at other kinds of algorithms, packing problems, sorting algorithms, And then moving on towards data structures. So those of you who know the textbook CLRS, Introduction to Algorithms, you do not need to know that textbook to be taking this course. In fact, we'll be going through quite a bit of CLRS in that kind of style, like more mathematical. Looking at amortized cost for analysis of algorithms and data structure operations, binary search trees. You've probably seen some binary search trees. We'll touch on those briefly, but then go on into the really, really cool mathy stuff like splay trees, and see why that's just unreasonably useful and interesting. Looking at heaps, so more data structures, hashing, different ways that you might go about hashing, a little bit of cryptographic hashing, maybe, I don't know. Look, we can talk about cuckoo hashing. There are really cool things that we can talk about. Huffman trees and suffix trees, different kinds of approximation algorithms, a couple of classes probably on that. And then round out by some more eclectic subjects, which will end up going into a bit more of machine learning theory. So I guess first some stuff that's more sort of computational, fast matrix multiplication and fast Fourier transform, how different kinds of sort of divide and conquer approaches can be really useful in algorithmic efficiency. A class that I'm just including because I think it's fantastic. It's called the probabilistic method. This is a method that comes from combinatorics. It was something that was popularized by Paul Erdős, the famous combinatorialist mathematician. And it's basically how to prove things in combinatorics using just random methods, and how random methods can be extremely powerful at proving statements about graphs and algorithms and other stuff. And I think that this way of thinking is really, really useful, even if you're not working on like Ramsey theory or something. Going on to compressed sensing, which is another area that really looks like magic if you haven't seen it before, and trying to provide intuitions for why that actually makes sense. Some quick look at information theory. And then moving on into really more machine learning meat, so graphical models, PAC-Bayes, and then some stuff with neural networks. So first, some basic neural networks that aren't really deep neural nets, like Hopfield nets and stuff like that. There's some really interesting math there that connects up to statistical physics, and then a couple of classes on deep learning theory. This is a very rough outline, and it's probably going to change to some extent. It's almost certainly going to change. It can also change based upon what you want. It's not going to completely reorient, so most of these classes will still be there. But if you think that something should be there, feel free to ping me. We'll have time at the end for questions, but feel free to let me know at any point if you think something should be covered, and it'll also adapt based upon how things are going in the course. So does anybody have any questions about that at this point? Okay, go on.
Sorry,
oh, sorry, yes, question.
Sorry, I was finding the unmute button. Seems like a lot of content. Do you know about how it will be dispersed, like one topic per class approximately?
Oh, those are classes.
Those are, okay.
Those are individual class lectures. So there will be 39 lectures, and that's how it's going to be distributed.
Very clear, thanks.
Yeah. They will probably get shuffled around a little bit, but yeah, that's just to give you a sense of the whole outline of the course. And again, I'm not going to be covering all of any one of those areas, just giving a flavor of some of the ways that math can be interesting there, and hopefully providing some intuitions for why things work. Okay, any more questions? Great. Logistics, whoops. There. So classes are going to be every Monday, Wednesday, and Friday from 4 to 5 p.m. And that's Montreal time, obviously. Office hours, tentatively thinking of office hours at 5 p.m. on Monday and 10 a.m. on Friday. Does anybody have a strong objection to that? Something that I'm missing? Reasons why that's bad. move them potentially if there's a problem with that. I'm anticipating that problem sets will be due the end of the day on Friday. So I was trying to make the office hours coincide with when I think people will be particularly wanting office hours. But I do encourage people to show up to office hours just in general. I think there'll be a really good chance to just talk through interesting things, ask questions, including very open-ended questions, work with other students. We'll get to that when we get to the problem sets, but I think that it'll be really good for students to be talking about problem sets and just talking together. All classes and office hours will be via Zoom. This is the Zoom link that will work for hopefully all of the classes. I will also set up a Zoom link for office hours, and you can get those Zoom links on the My Classes page. Some people do not have access to the My Classes page because only those who are either registered for the course or are auditors who are also at McGill have access to my courses. I'm not sure if I can get auditors who are not at McGill access to the My Courses page, but I will make sure that you get access to the materials and otherwise links and so on. Unfortunately, some of the discussions may have to happen via My Courses, so apologies to the auditors who are not at McGill. So apologies for that. Yeah, all materials and Zoom links will be at My Courses. So let me know if you have troubles accessing that and you think you should be able to access it. Grading. So the evaluations will be made as follows. 10% of the grade will be attendance at class meetings, with one exception, which I'll get to in a moment. And 10% will be participation in class. Now, that does not mean making smart answers during class. It means making an effort during class. So right answers, not important. Thinking, important. I encourage everyone to participate either by raising your hand and saying something or asking a question. Asking questions is a perfectly valid mode of participation. You don't have to answer questions. Or you can post in the chat. So making a diligent effort at meaningful participation, good questions or thoughtful answers. And then problem sets. There will be no exams for the course. It will be 5 or 6 problem sets, which will be weighted equally during the course. And that will be 80% of the grade. Now, an exception is going to be made for attendance and participation portions of the grade, but only for those students who are attending the class from some time zone that prohibits live participation. So for example, if you are calling in from Thailand, you do not have to participate live. You have to, however, let me know in advance, because otherwise you have to let me know now, basically, within the next week or two, that you won't be attending all of the meetings live. And again, that's only for people who are in a time zone that means that you can't attend. The reason why participation is so important and why I'm including it in the grade is not because I'm trying to be nasty here, because I'm trying to catch people out, but because I think it will help you learn. Like, both because showing up to class, I know when I was a student, that was really important as a part of my learning. When I skipped a class, even if I could watch a video afterwards, I didn't learn as well. So I strongly encourage people to show up if they can and participate, just because I think it's better for learning. That said, if it's the middle of your night, that might not be better for learning. So that's why participation is a thing here. Does anyone have any questions about this? And I'll get into problem sets in a moment.
Do you have an idea of when the first assignment will be due?
I expect that the first assignment will be due 2 weeks from this Friday. And I expect it will appear roughly Monday or Tuesday of next week. Okay. So you'll have about 2 weeks to work on it.
Yeah, clear deadline. I mean,
Yes, I'm
just trying to
sorry. I'm
plan.
sorry for everyone in machine learning who has an iClear deadline. There are deadlines. I
Yeah.
am not making an exception for homework for the iClear deadline.
Yeah, I was just asking well enough in advance to plan. Thanks.
Yes. We do not have class on Labor Day. That is correct. Monday is Labor Day, and that is a university holiday, so there will not be class. There's a question that there is an overlap between this class and advanced RL on Mondays, which is from 3:30 to 5:30. And switching between, Mandana is going to try to switch between this class and the RL one, but yes, all classes will be recorded. Okay, any more questions?
I have a question.
Yes.
I think I don't have access to my courses, so which channels do you prefer me to submit the homework?
Send me an email and explain the situation, and I'll try to get you access if you can get access.
Okay, thank you.
Any of there are several emails which are listed for me. All of them will reach me. My Mila email, my main McGill email, my CS McGill email, well, all of them will be fine. There will be deadlines for each problem set. Yes, the deadline, the problem set is not out yet. So you will get the deadline with the problem set. It will be around 2 weeks in which you can work on that problem set. Let me go into the problem sets. Maybe that will answer some questions. There'll be about 5 or 6 problem sets. I imagine 6, roughly every 2 weeks. They are important for learning the material. That is why all auditors who are in the class need to work on the problem sets and submit solutions, because this is part of the learning process, just doing the problem sets. Not necessarily getting everything right, but having thought deeply about them. They will be proof-based, and we will learn how to write those proofs. Not everything on the problem sets will probably be proof-based, but some of it will be proof-based. And I'm not expecting anyone has come in here knowing how to write proofs. That's why we're spending several classes on it right at the start. So don't be scared about that when we will also give you tips on how to write those proofs. The goal is to sort of teach you how to think in that way. I highly recommend starting them as early as possible, even if you don't have an iClear deadline. It's probably good to start them as early as possible. And discuss them in office hours. Come to office hours. One of the office hours will be right after this class on Mondays at 5. Just stick around and chat about the problems with other students. So collaboration policy. Collaboration is really important. I encourage collaboration. Now, there are different kinds of collaboration. I encourage talking to fellow students about the problem sets, working through ideas. That can be in office hours. I will try to make office hours be about collaboration between different students. Come just chat with people. Do make sure that you list all the fellow students you have worked with. And I'll show you how you should do that on the solutions. There will be a way to do that. So you're welcome to collaborate with people, but please list everyone you collaborated with. And if you list somebody as having collaborated with them, they should probably be listing you as well. However, written solutions have to be completely your own. You should not share proofs or overleaf or written notes of any form with other students. I'm pretty good at working out when material looks suspiciously similar between proofs. So please don't submit proofs that look very similar, even if you've changed variable names or something. And if 2 people submit something that looks suspiciously similar, I'm afraid both will have to get lower grades on that. But the takeaway from this should be just really collaborate, just don't share written materials. The goal of these problem sets is to learn, so that's why this collaboration policy is the way it is. I need to write this into the course outline. I still haven't updated the course outline with the latest collaboration policy, so currently ignore the course outline. Within the next couple of days, it should be updated. And I'll get to questions in a moment, but finally, LaTeX. So LaTeX is a system for typesetting mathematics. It is really a very useful skill for paper writing and other things completely independent of this class. It is required for problem set solutions, except for the first one. The first one you can do however you want. Please make it legible. I would encourage the first one to be written in LaTeX, but the first one does not have to be. Beyond the first one, all problem set solutions should be written using LaTeX and submitted as PDFs. Now, I will give you a template, a LaTeX template that you can use to write in your solutions. And I will also give you the source LaTeX for problem sets. So if there's some weird symbol on a problem set that you don't know how to typeset using LaTeX, well, you can just look at the source code for the problem set and work that out. I will also give you the source code for the slides. I anticipate all of my slides being in LaTeX. This is actually a LaTeX slide deck. It's using Beamer, which is the German word for what's the thing? The projector. It's a German word for projector. It's a LaTeX way to create slides. So I should give you the source code for the slides and for the problem sets to help if you are just learning LaTeX. I'm also going to share a couple of resources for learning LaTeX below. Figures do not need to be created in LaTeX. You don't have to worry about all these things like TIC-Z and XY-pick and blah, blah, blah. But they should be included in the PDF. So you should have they should be part of the same file as all of the LaTeX. So you don't have to draw everything using LaTeX or anything like that. Importantly, even though you have to submit p-sets using LaTeX, you don't have to have the LaTeX be perfect. Now, it has to be readable, but if you accidentally use the wrong symbol or something, it's not going to give you a lower grade. The goal is just to have practice using LaTeX and just make it more readable for us in grading. Here are some resources for learning LaTeX. I'm going to share the slides afterwards, so you don't have to copy these down. This is the website Art of Problem Solving has a guide to LaTeX, and there is a free online introduction to LaTeX on Overleaf. Overleaf, you should be aware, is basically a Google Docs for LaTeX. So this is often what I use for paper writing when I'm collaborating with other people, though it's not nearly as good as Google Docs, unfortunately. There was a question in the chat. Is there a Slack channel for this course? There is currently not a Slack channel for this course. I know that's something that people in Mila particularly used to. Not everyone in this course is at Mila. I might create a new Slack workspace. Would there be interest in that? That could potentially be a better way than having a discussion board on my courses. Interest? Post in the chat if you would like a new Slack workspace. We probably shouldn't actually use Teams because not everyone is a part of the McGill team, unfortunately. Okay, great. People like Slack. Then we will go, I will create a Slack workspace before the next piece that comes out. And you should feel free to ask questions there. And we'll have a channel for individual problem sets. Please do not have general, large scale discussions about the problems though. If you're collaborating on the problems, on a problem set, I don't want anybody posting the solution to a problem. That's bad. You're not allowed to do that. You are allowed to set up one-on-one and have a 3-person chat so you can nail down something, but it should never be one person saying, this is how you do this. And again, never share anything in written form. The goal of this is learning. Okay, that is all that I had, and I realize we're a couple of minutes over. Are there any questions? Apart from the problem sets, are there any textbooks or web resources you recommend for practicing or studying course material? I do not have any textbooks at the moment. I will let you know if there's anything that I recommend for a particular lecture or something, and I will try to have everything be digital if so. So I'm not expecting people to go out and buy a textbook now. Gilbert Strang for linear algebra. Gilbert Strang is a great, he's a great teacher and a great person. And if you don't know, he just came out with a book on linear algebra for machine learning, which is really cool for those of you who do machine learning. That said, only two class meetings will actually be about linear algebra in this course. That's one reason I'm not recommending a textbook. It's because we're covering so many different things. So you're welcome to read Gil Strang. He's great, but it's not required or particularly recommended for this course. Are there any more questions? In case you're curious about this picture, it's Pascal's triangle, which is how many ways there are of choosing in this case, like in this row here, if you can see my cursor, in the 5th row, how many ways there are of choosing one element out of a set of 5, 2 elements out of a set of 5. How many ways to pick 2 out of 5? That's 10. How many ways to pick 3 out of 7? That's 35, and so on. It forms this beautiful triangle, which we will look at in a few lectures. This is coloring all of the even entries in Pascal's triangle. It is forming a fractal, which is called Sierpinski's triangle. These are the entries. We will not, I think, prove this in the course, but you will have enough tools during the course to prove this if you want to. It's not that hard. More questions. Will you grade P-sets for audit students? Not totally sure yet, but we'll try to. Mathematics for machine learning. I'm not sure how to parse that question. If there was a question there, Melissa, then let me know. Oh, great. Yes. Thanks for sending the link for the mathematics for machine learning to everyone. Okay. Well, thank you all for coming. The chat is not saved, just so you know. So if you need to save anything from the chat after any lecture, do save that yourself. The recording will, and the slides and the source code for the slides will be made available both via my courses and for those who don't have access to my courses in another way. Expect an invitation to a Slack soon, and thank you all for coming. Looking forward to this semester with you all.
Thank you.
Thanks, everyone.
Next meeting on Friday at 4.
Yeah.
Thank you.
Thanks.
Thanks.